Welcome to this podcast, episode 3 about set theory by this middle school idiot. Set theory is the brainchild of Georg Cantor, and it was a theory that pretty much everything you can see, feel, think about, etc., including all numbers, they could all be organized into different groups with different criteria. For example, there's a set of cities in the United States, there's a set of odd multiples of 11 who have 10 factors. There's a set of books written in 2017 about the Holocaust. There's a set of stars more than 10 million light years away from us. There's a set of nothing and a set of everything. In 1874, set theory originated in mathematician Georg Cantor's paper. He theorized that numbers could be put into sets, groups with a distinct property. And in that paper, he also proved that infinities could be different sizes. However, his work was denounced by many other prominent mathematicians at the time, and humiliated and depressed, Cantor spent the latter half of his life in and out of sanatoriums, or mental and psychiatric hospitals. That, however, was not the end of Cantor's work. In 1891, Cantor had expanded on that 1874 paper by comparing the whole numbers stretching out to infinity and all the real numbers from 0 to 1. And the popular opinion at the time was that both have a value of infinity. And he made every whole number as some sort of index for the real number. And when he wrote down a new real number, he took the first digit of the first number and changed it, the second digit of the second number and changed it, and etc. That way, we all have a new real number that is different from his first number from the first digit, the second number from the second digit, and etc. And that number will appear nowhere on the list because, well, there is at least one digit that a new real number is different from the others on. And this process can be repeated pretty much forever. And this doesn't really just apply to natural numbers. Cantor has successfully proved that the infinities were different in size. Cantor's work on different size affinities was just the latest blow to mathematics, and others included non-Euclidean geometry. And so by 1900, math had fractured into two opposing and distinct parties. One was the intuitionists, led by Leopold Kronecker and Henri Poincaré. They dismissed and criticized Cantor and his work on different size infinities. On the other hand were the formalists, led by David Hilbert, and they embraced Cantor's work. After Cantor's discoveries, intuitionists were scrambling to find a flaw to it, a paradox, or some sort of counterexample. Welsh philosopher Bertrand Russell discovered the paradox first in 1901, Russell's paradox. He said, let R be the set of all sets that don't include themselves. Then does R include itself? If R does include itself, then by definition it can't include itself. If it does not include itself, then by definition it must. Russell had found a contradiction or a paradox of self-reference, which was a flaw in Cantor's set theory, but later versions of set theory, for example, the currently used Zermelo-Fraenkel set theory, had eliminated that problem. After all that, David Hilbert and the formalists knew that Cantor's work was brilliant, and Hilbert himself has said, I quote, "No one shall expel us from the paradise that Cantor has created." They wanted to create a completely formal and completely rigorous system of proof based on set theory, axioms, and logic. And about this new system that they created, Hilbert wanted three questions answered. Number one, was this system complete? Can all true statements be proven? Number two, was it consistent? Are there any contradictions? And number three, was it decidable? Could you find the answers to every single question you pose through the axioms? Hilbert was convinced that the answers to these three questions were all yes. But was he right? In 1931, 10 years after, or 3 years after Hilbert's declaration of the new system, Kurt Gödel, an Austro-Hungarian logician, had found the answers to Hilbert's first two questions in what we call Gödel's incompleteness theorems. The first proved that mathematics was incomplete. If Hilbert had formalized everything, some of the true statements would be omitted from the proof. The second incompleteness theorem proved that any consistent mathematical system couldn't prove its own consistency. As in, like mathematics right now, you just can't prove if it's consistent or not. The only way that you can tell is if some sort of paradox comes and the whole consistent theory just collapses like Jenga tiles. Hence, mathematics was definitely incomplete, and its consistency was questioned, at least in Hilbert's system. 5 years later, in 1936, came the answer to the last of Hilbert's three questions. Alan Turing, when he was still 23, he had invented the Turing machine, a theoretical computer. Turing didn't know if we could determine whether a Turing machine would stop or halt, as he called it, given a specific input and a specific code. Turing had determined that the answer was no, and then he linked it to Hilbert's third question. The halting problem, or what it was called, Turing proved, could also show the same results for other problems. For example, the twin prime conjunction, whether there were an infinite number of twin primes who had the difference of two. Hilbert had failed. He had created an incomplete, maybe consistent, and undecidable system of mathematics. However, he succeeded as well. The new system, the current system, it was overwhelmingly unproblematic, and it had relied on set theory. Other tools have been made to elaborate on set theory, for example, Venn diagrams, and also Hilbert's axioms and his 23 problems. And set theory now is its own branch of mathematics. Set theory had also led to the invention of the computer, quantum computing, and AI through the Turing machine, and later on ENIAC created the first working computer, a physical computer, created by John von Neumann, sorry for the butchering, and Alan Turing himself.